Hello, students of science. Let's talk about the scientific process. Your target is, can you identify and conduct a controlled experiment? Let's get started. So, the scientific process. You may have heard it called the scientific method. I prefer the scientific process. It starts, of course, with a purpose or a question. It's more or less, what's the problem? Why are we doing something like this? Next up, you're going to move to something with a hypothesis. A hypothesis. You've probably been coached to say it's an educated guess. I don't like that term. I don't like the guess that it implies. It's more of a testable idea. And the guy has narrowed it down to two hypotheses. Either the spider grew or they shrank. Both of those are testable ideas. You could do other things to find that out. And importantly, with a hypothesis, it should be able to be wrong. You should be able to disprove it. As Carl Sagan may have said, nice hypothesis you have there. It'd be a shame if someone were to test it. I'm going to show you guys a bunch of different hypotheses, and what I want you to do right now is pause the video right here, and I want you to write down one good hypothesis and one bad hypothesis. So pause the video, write down a good hypothesis and a bad hypothesis. All right, I'm assuming we're back now. Let's go through these one at a time. This first one here, the plant that receives bleach instead of water will grow taller. I'd say that's a good hypothesis. That's a terrible idea. Don't give bleach to plants, but it's a testable hypothesis. I think that if I give bleach instead of water, it will grow taller. It could be wrong. It probably is. But that's the important part about a hypothesis. Next up, donuts for breakfast will improve student test scores. That is a fantastic hypothesis and a fantastic idea, mostly because I want people to bring me donuts. But it's specific and it's testable. Bring me donuts, that will see an improvement in student test scores. I could test that and it could be wrong. I hope it's not. I want donuts. Next up, ladybugs are a good natural pesticide. I'm going to say no. I don't really like that as a good hypothesis. It's not specific enough. It's not really testable. Like, what do you mean by good? I want something more specific. I want to know ladybugs will decrease the percentage of aphids on the plants. Something like that is specific. Good, not a really good term there, ironically enough. Next up, all daisies have the same number of petals. As weird as it is, that's actually a pretty decent hypothesis. Could you test it? Yep. Could it be wrong? Yep. Is it wrong? More than likely. But that's easy enough to go out and come up with a test for, and definitely come up with some kind of answer, and it could be wrong. How about here? Some people are more likely to donate to charities than others. No, not a good hypothesis. Why? Because of course some people are more likely to donate to charities than others. That's like saying some people are taller than others. Well, duh. I mean, you haven't learned anything. It's not specific enough. I mean, yeah, you could test it, but in the end of this, you would say, yes, some people are. But that's, obvious. Not a good hypothesis. How about here? Rats that eat poison will run further on a treadmill. Actually, that's a good hypothesis. And a bad idea. Please don't give them poison unless you have like a rat infestation. But it's very specific. I give them poison, they will run further. Could it be wrong? Yes. Is it wrong? Yes. Next up, why do some people drink Mountain Dew, like myself, and others do not? Not a good hypothesis. Why? It's not really testable and specific. It's more of a question than anything else. I really don't like that one. And down here, some clouds reflect more light than others. Again, not really a good hypothesis. Yeah, of course some are going to reflect more light than others. Again, that's the way things work. Not specific, not testable, not a good hypothesis. Let's go into the scientific process a little bit more. So we already had a purpose, we already had a hypothesis. Next up, we need a controlled experiment. A controlled experiment is where everything is going to remain the same except for one thing. That one thing happens to be the independent variable. Next up, we need to record and analyze our results. This is looking at, hey, what did you see? What did you measure? That sort of thing. It should be in some kind of a graph or table. As Adam Savage, one of the Mythbusters, says, remember kids, the only difference between screwing around and science is writing it down. Next up, we need to have a conclusion. We need to check our hypothesis. How well did it do? Was I right? Was I wrong? I need to find out. And finally, we need to summarize your results. I always like to say that summarizing your results is like you're trying to describe your graph or your table over the phone, something that someone else could understand, but it's again specific enough to actually include the important points of your data. You got your hypothesis, you do an experiment, you look at results, you come back and you form some conclusions, but again, it's not over. You still need to go back, re-examine those hypotheses. Maybe you weren't entirely right. Maybe there's more you could do. The scientific process or scientific method is never over. They're constantly trying to find things that are wrong with it, things that could be improved. Remember, it's easy to make assumptions about things in the world, like, puppies strapped to missiles, but good science requires testing. One of my favorite quotes out there, so the universe is not quite as you thought it was. Well, you'd better rearrange your beliefs then, because you certainly can't rearrange the universe. As a baseball player named Oscar Gamble once said, they don't think it be like it is, but it do. Wise, confusing words. So in our controlled experiment, as I mentioned before, we have the independent variable. That's what you're testing, what you're changing. And of course, the dependent variable is what you measure. So in this particular experiment here, I have two groups of plants, A and B. What I'm going to be testing is probably, let's say, fertilizer. So the independent variable here is going to be the fertilizer. The dependent variable is going to be, well, what I'm measuring, which in this case is the height. So independent variable, type of fertilizer. Dependent variable, height of the plants. And next up, we have a control group. This is the group that we compare results to. You could summarize the control group in one word, comparison. It's all about what I'm going to be comparing everything to. Otherwise, I don't know. If all I have is group B, and I just gave them fertilizer, I don't know whether or not they grew any better. I need something to compare them to. That is the purpose of group A, my control group. Here, the independent variable, fertilizer or no fertilizer, is not changed. This is sometimes called the normal group. So here we have two mice looking on two other mice, and you can see these ones look, well, normal. These ones are jittery and shaky. Well, I guess we're in the control group. So here we have the scientific method versus the mad scientific method. In the scientific method, you ask a question. You construct a hypothesis, a testable idea on that. You test it, you experiment, and you draw conclusions. Mad scientists, well, they don't really do it in the right order. They start with a conclusion, then they do a test, then they come up with a hypothesis, and finally they ask questions. It's kind of backwards the way it should be. So go with the scientific method, not the mad scientific method.